Hey, thank you for the introduction. So today I want to present our joint work of the University of Warsaw and the Applied Crypto at TU Darmstadt. So to start off with the light motivation, when we think about cryptocurrencies, then there is a problem that blockchains do not scale very well. So blockchain is the main ingredient for cryptocurrency, and it consists of a chain of blocks where every block contains transactions. So when Alice wants to send a transaction to Bob, she proposes this transaction to the underlying cryptocurrency network, which will eventually publish this transaction in a new block of the blockchain. So Bob can at any point then look in the blockchain and see if this transaction was included and knows whether he got the money. So the good thing about this technology is that it allows payments without a central intermediary like a bank. But the problem is that this is actually not quite as convenient as we would like it to be. In particular, whenever the decentralized network of the cryptocurrency has to create a new block, this takes actually quite some time, and it might take minutes up to even hours until Bob knows that this transaction has been included and confirmed. On top of this, the cryptographic network underlying the blockchain wants to be paid for this service, so there's transaction fees for every transaction. This might not be a problem when you want to send thousands of dollars, but when we talk about very, very small payments, this is actually quite an issue. So the goal of our work is to change or to adapt this technology to allow microtransactions. So really, really small, really fast payments that do not require many fees, that can be executed almost instantly, that are as secure as a normal transaction over the blockchain, and that do not rely on any assumptions on connectivity to a network. So how do we want to build this? We want to build this with smart contracts. Smart contract is a piece of code which can be deployed to a blockchain. Some cryptocurrencies, most notably Ethereum, specialized on smart contracts. And parties can send coins to a contract which stores this money and can be triggered to execute code or evaluate data and then pay out these coins again. But every time a contract is triggered, that's again a transaction, meaning we have to wait quite some time until this happens, and it costs again money. In this case, the transaction fees are called gas. So to give you a very short overview about our contribution, the goal is to get microtransactions to cryptographic currencies. And we want them to have these properties to be cheap, fast, offline, and secure. The whole system should be based on smart contracts, and it should work in a hub-like network where everyone is connected to everyone else with at most one hub. In particular, we are going to propose two types of payment channels. The first one is a direct connection between two parties, which is based on a smart contract on the blockchain. And the second one is a virtual channel, which works in this hub network and relies not directly on the blockchain, but on two underlying ledger-based channels. So after I gave you a short motivation, I now want to show you how to build such a ledger payment channel. These kinds of payment channels have been proposed in other literatures as well. Most notably, you might have heard about the Bitcoin Lightning Network. And the idea is always quite similar. You have three phases of a channel. First, you have to open it or fund it. Then it can be updated. And last but not least, it has to be closed again. So if Alice and Bob want to open such a channel, they create a channel contract and submit their funds into it. So Alice locks CA coins and Bob locks CB coins. Now that the channel is funded, we actually can forget about the smart contract for now. The channel can be now used off-chain without talking to the blockchain, the cryptocurrency, or the smart contract. And the state of this channel is always displayed in a tuple which consists of the balance for Alice, the balance of Bob, and a version counter, this V. So the initial balance that Alice and Bob have is the coins that A paid in, the coins that B paid in, and the version 0. If Bob now wants to send some money to Alice, let's say 5 coins, he proposes a new state where he has 5 coins less, and Alice has 5 coins more. So the new state of the channel has version 1 and updated balances. He proposes a state to Alice by sending her a message, and what's important now is that he also includes a digital signature over this new state to show that he approved with this. Alice will then verify that he computed this correctly and confirm this transaction by sending her signature back to Bob. Now both of these parties have an updated state with version number 1 and the counter signature of the other party. So they can actually forget about the old state. They only have to store the latest state of the channel. And what's really nice about this setup is that at this point they can do this as many times as they want. They can just send these 2 messages to send a payment, and they can do this as many times as they want and as fast as they can basically send 2 messages. They can even be connected over some near-field communication technology. We don't even need the internet for this, basically. And it's also secure. And why it's secure gets a little bit clearer when we look at the 3rd step, the closing step, where we have to go back to the channel. So Alice proposes her latest state to the channel contract, which then first of all verifies if this is correct state. So if no money has been created and it has been approved by both Alice and Bob. But then the channel doesn't actually do anything. It basically waits until Bob also sends his input. This is important because Alice could have lied about the latest state and sent an outdated version where maybe she owns a little bit more money than Bob. So Bob now has enough time to see that his input is required on chain and send this message. He also sends his latest state, and if it's valid, the channel contract can now compare these 2 states and select the newer version of the 2 of them and pay out the balances accordingly. So as you can see, this kind of channel is secure whenever the parties closely check whatever they sign, because then they have the guarantee that they can always enforce whatever has been signed to them. So if Bob promised a payment to Alice, she knows she can enforce it this way. So now let's go a step further and look at how we can build a virtual payment channel from 2 existing ledger payment channels. This is also something which has been looked into in the literature, and most notably in the Bitcoin Lightning Network paper. And it has been considered how to route a transaction over an intermediary. So in this case, the intermediary here is called Ingrid, and we have 2 channels, one connecting Alice and Ingrid, and one connecting Ingrid and Bob. And now we can use her to route a payment. So in the Lightning Network, this is called hash time lock contracts. And it works in a very simplified manner as follows. Bob tells Alice that he wants to send her a payment. Alice then goes to Ingrid and says, hey, look, Bob wants to pay me some money. And Ingrid says, okay, I promise you that I will give you that money if Bob gives me the money first. And then she talks to Bob, who will eventually send her the coin. And then Ingrid fulfills her promise by sending another coin to Alice. So this is really nice because it allows Alice and Bob to send payments without going down to the blockchain, without opening a new channel or all this kind of stuff. But the problem here is that it doesn't quite allow us to have microtransactions, because every time we want such a payment to happen, there's a lot of communication going on, and Ingrid is highly involved. And of course, she wants to be paid for this service. She also has to be highly available for this, and her availability limits the throughput of this kind of payments. So what we want instead is actually build a new layer, a new channel between Alice and Bob, using Ingrid as backup, but actually not involving her. And this again gives us some nice features that we wanted to have. Micropayment ready channel. So how do we build this? Well, it's actually quite similar to before. We have the open, update, and close phases, but instead of going to the blockchain for the open and close, we now go to Ingrid. So Alice proposes to Ingrid, let's update this channel between us in the following way. 1 coin is subtracted on my side, 1 coin is subtracted on your side, so the 2 coins that are suddenly now not in the balances are locked for this virtual channel between Alice and Bob. Ingrid waits until Bob also confirms or also proposes such an update on the other side, and then agrees and says, okay, great, let's open such a channel. At this point, again, we have a new layer, a new channel between Alice and Bob, and Ingrid doesn't have to be involved at this point. What they have to know, what Alice and Bob need to know for this is the confirmation from Ingrid that she agreed to opening such a channel. And the new channel is funded now from one side, from Alice's side with 1 coin and from Bob's side with 1 coin as well. The update is pretty much identical to what we've seen before. So we have a channel state, and if Bob wants to send his coin to Alice, he proposes a new state where she gets this coin, sends a statement and a signature, and so on. So again, they do the update as many times as they want. And once they want to close the channel again, they go down to Ingrid. Alice sends the latest version of the virtual channel state to Ingrid and includes her own signature and Bob's to say, look, here's the proof both of us are completely fine with this state. Ingrid now needs to make sure that this is the latest state, so she again also asks Bob. If Bob sends the same statement, she knows that they agree on whatever distribution in the virtual channel should have happened. And then she proposes an update to the underlying ledger channels. So to update these 2 channels in the following way, that the 2 coins that were blocked before are now unlocked in the favor of the left side. So in this channel, Alice gets the 2 coins, which means that Ingrid actually lost a coin. But that's not a problem because on the other channel, she actually gets the 2 coins that were locked before in her favor, and Bob lost 1 coin. So Ingrid stays financially neutral. She didn't lose any coins. Bob, on the other hand, has a coin less, and Alice has a coin more, so the payment happened. This financial neutrality is actually one of the important security properties that we want to prove in our work. So this is one property. Another one is that all of the parties involved in a channel always have to have consensus on whether a channel has been opened, updated, or closed. Third property is that whenever someone promised to pay a person by sending a signature on a new state, the other person has the guarantee that you can enforce this payment. It has guarantee payout. And for Ingrid, it's very important that she knows that at some point, the coins that she locked for Alice and Bob can be unlocked again. And for this purpose, the virtual channel has now another property, a validity. So a fixed time for which this channel is alive, and Ingrid cannot do anything about this, but after this validity passed, Ingrid can request to close this channel. And of course, this has to hold even if all the other players collude. This is only an informal overview of the security properties that we analyzed, but in the paper we did a thorough modeling and you see proof of these protocols. Let's also look at the performance of this. So we compare 3 scenarios. First, the ledger channel, which is opened and closed on-chain, and updated completely off-chain, directly between Alice and Bob. So here, this blue color means we get this nice micropayment properties. In the closing, we have actually 2 different possibilities. The first case is where Alice and Bob agree and no problem occurred, and the disagreement case, where suddenly some problem happens, one person goes offline, or they start sending different states. So we implemented proof of concept, smart contract for this, and measured the costs for this. Actually, due to the rapid changing in cryptocurrency values, these values currently halved. And so a ledger channel has to be, opened and closed on chain, and this can take either 50 cents to close or 55 cents, because disagreement is always a little bit more expensive than agreement. In the Lightning construction, the hash time lock network, we don't really have open and close of a channel, but we can send transactions via Ingrid. So every time Ingrid is involved. And only in case someone of them disagrees, goes offline, or starts misbehaving, we have to go down on chain. The same happens in the virtual channel. Only in the very worst case we go on chain, but the channel can be opened and closed with Ingrid and completely updated off chain directly between Alice and Bob. So here we have again the nice micropayment properties. A nice observation in this case is that the fee model for Ingrid actually changes a little bit in these 2 cases. So in the hash time lock network, Ingrid is paid for every transaction that is routed over her. So for every transaction she gets a fee. In the virtual channel, she's paid for the time that she has to lock the money. So for this validity time. So the applications when which channel makes sense also changes. Okay, now I want to give you a quick summary because I'm running out of time. In this work, we proposed a new formalism for payment channels, and a new construction called virtual payment channels, which can be opened and closed without going to the blockchain and can be updated without the intermediary. Virtual payment channels and payment channels have the same assumptions as the underlying blockchain system, so we trust the majority of the network, but not anyone else in particular, especially not the other side of the payment channel or Ingrid. We also proved that this is secure in the UC model, and we've been working on some extensions. The first one is where we said, okay, payment channels is cool, but since we are in a smart contract world, we also want smart contracts to run inside of channels. So that's called a state channel. And this has been presented at CCS last year. And another extension is where we went from the two-party case to the n-party case. And this has been presented at Eurocrypt today, actually. So, yes, thank you very much for your attention.
Thank you very much. So we have time for questions.
Thanks for the great work. I have a question regarding your comment on being offline and exchanging data without having an internet connection. Obviously, one of the two parties can have an internet connection and adversarially close the channel. So how do you suggest we mitigate that? Is it through watchtowers, or what is your solution here?
Yes, so that's right. The offline assumption is only short-term. So you have to, from time to time, look at the blockchain to see if the other party started closing the channel. For the direct payment, you don't need a connection, an online connection, but for the security of the underlying protocol, you have to specify a time interval that you have to look at the blockchain. And watchtowers is actually a nice idea which helps to outsource this service of watching the blockchain to a third party. And that's a very interesting ongoing work. Yeah.
Hi, Luke Desautel from Samsung Research America. This may be a naive question, but are there any potential timing exploits when someone makes a payment? As you said, the value of cryptocurrency changes very, very fast. So could you get some cooperation to only accept the payment or only allow the transaction to come through if the currency has gone up? This would be similar to getting an option. I have the option to receive your money, or I'll just wait and let it time out if the currency has not raised in value while I'm working on receiving the transaction.
Okay, so yes, that's an important issue that if you have, so a payment channel is where you lock money for a certain amount of time and then you only talk about absolute coin values, not about the actual US dollar value of whatever you're talking about. So if someone proposes a payment which is unattractive to you, you can always say, no, I don't want to receive this payment and not confirm it. Yes, so you have to, if you promise money in the first time and then you, at some point, and then you wait a lot of time until the price of Ether increased a lot, then this money that was promised to you might be worth much more than at the point where it was promised to you. And there's not much you can do about it except for closing the channel whenever it starts becoming unattractive.
Hi, I'm Armin from Avast. Thanks for the great talk. Would it be easy for Ingrid to do a conversion between different blockchains or even different cryptocurrencies?
Yeah, that's a very interesting question. And yes, this is possible. It's not in the works right now, but people are working on this. And there's, especially with the virtual channel, there's a nice idea of having like a Bitcoin channel and an Ethereum channel and then a virtual connection between two parties in different currencies.
So we are running out of time. Thank you very much again.